Yeah, we are live now.
Oh, great. Okay, great. So good evening, everyone, all the viewers in YouTube as well as in Facebook. Welcoming you all to the 41st session of Vertical 3. As you all know, we focus on practical sessions on open and proprietary software. Today, the session will be from 6 p.m. to 8 p.m. Myself, Giri, one of the coordinator of Drug Discovery Hackathon. Kindly please note, do not share any personal details like email address or any other details during this online meeting via YouTube chat. If you have any queries related to registration, official registration of Drug Discovery Hackathon, the email address is given in, so you can write to them. Like many have written, like you have issues of individual team-based registrations, and also you could refer to this particular email address with the screenshot. And once you get access to virtual tool room, all the queries can be written to DDH support at cdac.in. Sure, you will be getting soon, either today or tomorrow or coming days, you will be getting more details about how to access the softwares through the partners who are offering different tools. All of you kindly type your questions in the live chat, and during the Q&A session, we will try to answer the question. And this is how the virtual tool room registration form looks like. You can either choose one or multiple software, so there is no restriction, or even you can opt out from this selection of using virtual tool room. Now, today's topic is docking workflows and electrostatic complementarity in Flare. And I'm very happy to introduce our speaker, Dr. Nathan Kidley. He's a senior application scientist at Cresset Software. He's having a PhD in computational chemistry at the University of Exeter, UK. Later, he joined Syngenta at Juliet Hill, where for 14 years, his work primarily focused on lead finding optimization projects and also for small molecule active ingredient research. Nathan's experience spans writing chemical standardization rules to using molecular dynamics and to drive conformational changes. At Cresset, Nathan's responsibilities include training and supporting customers, enabling them to achieve their scientific goals through the use of Cresset's ligand-based and structure-based software solution. So today, Nathan will be giving his talk. Over to you, Nathan. Thank you.
Thank you very much for the introduction.
You could please share your screen. Yeah.
So most of the session will be a live demonstration, but I do have a few slides just to introduce and share some information to you. It's easier to do that through the slides. So we'll start off talking about docking workflows in Flare. All of the docking applications can actually be used command line as well if you need to increase the throughput. But I'm just going to be talking about using the applications within the Flare GUI. So in Flare, we have an application called Lead Finder, and that's been optimized, obviously, to reproduce crystallographic poses as accurately as possible, and has a number of detailed different scoring functions that I'll talk about in greater detail. There's also an option that helps prepare the protein, and that's part of a protein preparation step within Flare. But essentially, all you need is a 3D protein structure and some ligands, which ultimately get turned into 3D, and obviously then you use the docking function to put them and assess their fit into the active site. The protein is rigid in all workflows in Lead Finder. So the general workflow, as I mentioned before, is you start off with a protein structure that's prepared and optimized, and there is an automated workflow with that. But of course, expert knowledge can be used to make changes as needed to the protein in active site. Then you define a grid So that's the area that you'd like to explore docking your compound within in the protein active site. And finally, you take ligand structures and then you dock those into the and then assess them using the scoring function. So lead finders docking is based on a genetic algorithm to sample the conformations of the ligands and also the placement within the active site. It's been extensively modified and tuned to perform molecular docking well. And what happens is a number of random conformations and placements of ligands within the active site. These are then, this initial population is increased by introducing optimizations to the random individuals and scoring them. And the most fit ones from that pool are then used, and then they have further, they are then clustered. And then after the clusters are created, we call them niches. Any compounds within those niches are kept. Any that are just outside those niches are rejected. And the best niches all are scored. The best ones are kept, and then the evolution process continues. Continues through, and then you ultimately ending up with a nice optimization and expiration of the active site. So just a quick mention on the scoring function. So LeadFinder uses a semi-empiric scoring function. The function is these functions have the same set of energy contributions, but are weighted differently to generate these three different scores. So we have a rank score, a delta G score, and a virtual screening score. There are also a number of different docking workflows within Flare. So there's a conventional docking approach. There's also a template docking, which is considered to introduce a bias for the docking results if you have a congeneric set of compounds. So the molecules to be docked are aligned by a substructure to a template ligand, and then the aligned conformations are used to seed the docking runs. And that generally leads to improved docking results. In Flare, template docking is an option for both conventional docking workflow and the next one that I'm going to talk about, Ensemble docking. So Ensemble docking is Flare's approach to deal with protein flexibility. And in this case, what you do is you actually dock into multiple conformations of the same protein. So it isn't a true flexible docking approach, but you have a number of different protein structures with different conformations that you can dock into. We also have a covalent docking workflow, and that allows you to, it's a new module enabling you to predict the binding pose and interactions of covalent inhibitors. This class of ligands derives their activity from forming a covalent bond with the target, but also they maintain and have a network of non-covalent interactions within the active site of the protein. In addition to this, you can add constraints, so you can select atoms within the protein to ensure you have those interactions to generate the best quality poses. There are a few different methods available that allow you to get higher throughput or more accurate results. So in the figure here, I've got a normal result. So this is the default setting, and it's been optimized to provide an accurate and exhaustive set of results. And on the right, I'm showing an accurate but slow result. And actually that uses the default settings but it actually repeats the experiment independently 3 times and keeps the best poses. And that helps enhance the sampling of the genetic algorithm. In addition to the normal and accurate but slow options, there's a quick option which is designed for use in virtual screening. It is faster. It produces it's a slightly less precise docking algorithm, but it's recommended for use, obviously, in virtual screening docking runs. We've got large libraries of compounds where speed is very important. Finally, there's a very accurate but slow, and this applies extra precision to the docking quality. It uses the most rigorous sampling and scoring algorithms within LeadFinder to increase the accuracy and reliability of the predictions at the cost of slightly slower speed. And it also repeats the docking 3 independent runs to help, again, enhance the sampling. There's also a score-only option, which calculates the scores without from a pre-given pose. So just a couple of quick slides, and then we'll get into the demo. So template docking. So if you just use the conventional docking result, starting from 2D structures of the ligands, this is the kind of result you would expect to see. So there's all of the poses look reasonable. There's a certain amount of fuzziness in terms of the exact overlay of all of the compounds. But if you use the template docking, because you do a ligand alignment onto a reference compound that uses the substructure MCS algorithm, the result you can expect to see from the results are actually a much tighter superimposition of compounds from doing the ligand alignment before the docking, and that's all part of the template docking approach. So this is much more useful if you've got a predefined chemical series you're working on and you've got co-crystallized structures of a representative of that ligand set. Covalent docking. So what we do is we take the electrophilic compound and we perform a chemical reaction to it. These are the currently defined covalent warhead that we support. We can add additional ones to that. And so what covalent docking actually does in terms of its workflow, as I said, it takes the reactive electrophilic compound, it docks it into the active site where the nucleophilic amino acid that's been defined and performs a chemical reaction to generate a product compound with a pseudo-covalent bond. So what that really means is the ligand is not formally covalently bonded to the protein, but is bonded to the nucleophilic atom from the defined amino acid that's been which is protonated. So an example of this is a Michael acceptor docked into an active site with a cysteine residue, where the cysteine will have reduced the compound with a protonated sulfur atom attached. The sulfur atom will have the same coordinates as the sulfur of the cysteine in the active site, and other reactions and amino acids behave in a similar manner. It should be noted, however, that FLAIR does not infer reactivity, and we'd recommend a QM-based approach for a full study of reactivity. So the residues that are supported within covalent docking are cysteine, lysine, serine, and tyrosine. Just a brief mention of ensemble docking. So really this was developed because many docking assumes a rigid active site, which is unrealistic. So Ensemble docking is a module of Flare for considering active site flexibility when you've got alternative active site conformation to the same protein. So the lead finder docking algorithm is used within a workflow similar to that of standard docking, but enables the inclusion of multiple proteins, each corresponding to a different conformation of the active site in the same docking run. The proteins can be used in an ensemble docking experiment, must be aligned together with in 3D, and that can be done within Flare. Template docking is also available as an option within Ensemble docking. And this is the kind of result that you would see, whereby actually you've got ligands with the results. So here we've got the different poses expanded, and you can actually see the different proteins that have scored for been selected for those poses, and then they have the associated scores with them. And that can be shown in a blow up here, so you can see the different PDB codes. Finally, you can add constraints to atoms within the active site to ensure you get relevant poses. So here you can see some docking constraints have been added to the protein. The hydrogen bond interactions. So we've got a carbonyl, an oxygen, and a hydrogen from a backbone amine from the amide. And that's easy to do in terms of you can add constraints. You can use this menu and you can add a constraint, and then you can change the strength of it. So that's all the introduction done. What I'd like to do now is actually show you docking for real. So I've got Flare open here, and I'll just open a file that I have already set up. So what I'm going to do is just read in a PDB file, a Flare project file with some PDBs that have already been prepared. So these different proteins here have actually already been read into Flare, prepared, and the crystallographic ligands extracted, and they're present here in the ligand table. The example I'm going to use is actually a Bruton tyrosine kinase protein and ligands. So now I've got my proteins and crystallographic proteins and ligands loaded. I'm going to read in some files for docking. And I'm actually going to read in a 2D SDF file. So I'll load that. And I have a few options in terms of preparing that as well. I'm going to take the rule-based option. Let's read in those files. So I've got this warning saying them to be, they need to be in 3D. They're currently in 2D. And I can either automatically put them into 3D, or the actual docking workflow can do that for me. So I'll say no for now. And read in those ligands. So now I've got my crystallographic ligands, and they now actually have read them in as 3D. And what I'm going to do is I'm going to dock them. So docking is a ligand application. So in our menu set here, we've got a different set of options and in the ligand menu, we have, this is where the docking options are for you, because they are a ligand defined workflow. So I'm going to just do conventional docking. So I'll click that, which opens up this little menu here. So within this menu, I can define the method here. So I can go from quick, which is for my virtual screening choice, to normal, which is the default one, to these more accurate methods, or I could actually just select and use score only. I'm going to use normal because this is a demonstration, but I would recommend you, if you don't have a large number of ligands, using the more accurate options gives better results. So what I'm going to do is I'm going to select the ligands, and here I can define. This is how I can select what ligands I wanted to use. I could either take the undocked ligands, which Flare can identify that these are not docked because they don't have a protein associated with them, or I can just select them and have them as the selected ligands. I could also define a ligand to do some use as my reference to do template docking. I'm not going to do that at this stage. I need to select a protein. So what I'm going to do is I'm going to select this specific protein, and I'll actually just display it as well. And now I have my protein. I think I've read in the results. Okay, so now actually I read the wrong file in there. So I just want to dock these 2D ligands in. So I've selected them here, and I want to dock into this protein. So I've shown here is my crystallographic ligand in the active site. So to generate the grid, I can either pick atoms in the protein. So I can use shift and left click and select atoms to actually grow a grid, which will allow me to then dock ligands within. And this can be very useful in terms of actually defining a grid if you don't have a co-crystallized structure in your protein. Or if you do, you can actually use the co-crystallized ligand to actually define the active site for the grid. So what I'm going to do is I'm going to do that. So I'm going to take the crystallographic ligand, which is this one, and you can see I've now defined my grid, my docking run. Finally, in the chains area here, you can see I'm including the chain A, which is a protein. The other chain, if we look here, is actually some additional cofactors, and I'll include those. I currently don't have the water checked for my docking run. So although the water is present in the 3D display and in the protein here, it will not be used for docking because it's unchecked. If I wanted to use water in the active site for docking, I could simply check it. But if I do that, I have to spend some time to consider which waters might be displaced by changes to my designs that I'm trying to dock in the active site. Because if they're included, then they are part of the protein, and the sterics will clash with the ligand if you try and superimpose atoms onto it. So I'm going to actually dock without water present, and I'm going to include this option here where I'm going to make copies of my ligands. So my results will be new entries in the protein ligand table, and the original 2D structures will be kept. If I want to look into more options, I can by clicking on this button here to show more options. And here it actually gives you more information and allows you to customize your docking run much more. And you can see if I change from normal to accurate but slow, actually the number of runs has increased to 3, but all the other options have actually remained the same. As I said, I'm going to use the normal method, but you can use the more advanced methods. And in addition to that, if you look at quick, you can see that some of these settings have changed, and that's really to be used for virtual screening. You've got the very accurate but slow method as well, or the score only option. And the score only option has some extra bits, so you can actually score it specifically as is without it changing, or you can allow some small optimization of the ligand in the active site. So I'm going to now click Start to start the docking run. And because we haven't done docking before in this project, I have to generate the grid itself. That's relatively time consuming. But actually, once a grid has been generated, it's saved within the Flare project, so it doesn't need to be used again, created again, and can be used without having to regenerate. But what I'll do in the interest of time is just cancel that and load in the results. So I'll just cancel that, but you can see the performance, and that's just running on my laptop. And what I'll do is I'll just read in the docking results from doing that experiment. So here I've got my crystallographic ligand shown in the active site colored in red. I've got my results here with the _D appended to them. So actually I'll just apply the filter so I can just look at the ligand results. And if I select them all, I can actually see that all of them look quite good except for one. One seems to be not have an ideal result in terms of the fact that the ring is flipped compared to the others and compared to the crystallographic ligand. So what I can do is I can actually look at these results. So I'll just expand this ligand table. And here you can see I have my scores from my docking. So I have 3 scores. I have a rank score, and that's been optimized, as I mentioned before, to identify the best crystallographic ligand pose. Then I have a delta G score, and really that's conceived for use in a congeneric series where you're comparing design, small changes in ligands to try and identify which are picking up better activity. And I've got a virtual screening score, and that's been optimized to try and identify actives from inactives in that context. All of the scores are an energy score, so a larger, more negative score is better. So if I look down to this ligand here, which seems to have a lower score than some, not the lowest, but this pose is clearly different from the others. If I expand this little triangle next to the index number, I can actually see a map up to, in this case, because I asked to see only 10 poses, I can see 10 poses. So some of the others may have less examples. So this one has only 8 poses that fulfill the docking score criteria. But you can actually see all of the different scores for each of the poses. In this expanded view, you can actually look at the different poses. So already we've got the second pose is actually much better and is in line with the results of all of the other ligands that have been docked and the crystallographic ligand. And actually, if you look at the scores, you can see the scores are very close between the pose that we don't like and the pose that we do like. The delta G score suggests this is the better pose, as does the virtual screening score. But there are a number of other different poses you could look at as well. And you can just look at those and sample your way through. As we like second pose and we'd like to make use of that and not use the top pose in terms of visualizing it, if we check the circle here, when we collapse all the poses shown, it's actually now the selected pose and not the best scored one. So it's a nice way for you to be able to look at the different poses, identify the right ones if there are differences, and then use that instead. If you wanted to minimize or further optimize these poses, what I'd recommend doing is actually you can duplicate a pose out of Flare. So if we wanted to minimize this pose in the active site, if I selected it and right-clicked and copied the pose to a new ligand, that would enable me to perform additional, here it is, additional work on that ligand and not delete my docking results. If I just did a minimization on from this pose here, all of my other all the other results for docking would be lost as this single pose was minimized. One of the other things you can actually do, which is a very nice feature within Flare, is you can actually take all of your ligands, and I'll just highlight them all and grid them out so you can see them, and turn the protein off to make it easier to see. I can actually color the atoms by their docking contribution. So this is what I'm going to do here. And actually the default settings is the values are -2 to 0. I recommend using -1 to 0. Seems to be a better contouring level. And here you can see how each atom contributes to the docking score. The crystallographic ligand is colored red because it doesn't have a docking score, and the coloring scheme by default is a rainbow from red being bad through to dark blue being good. So that's actually just the conventional docking workflow. Of course, you can have the protein on and look at the interactions that are made within the active site, and later we'll actually look at the electrostatic complementarity, and that is a nice add-on in terms of looking at crystallographic docking, and understanding which interactions are really good or which could be further changed to improve the activity of the ligands. So with that, I'm actually going to show you how to use ensemble docking. So in this example, we just docked into one ligand, one protein with all those ligands. So what I'm actually going to do now is I'm actually going to set up and run the ensemble docking. So I'll just turn off my filter so that I can see my 2D ligands. And no, okay, this is it. Yep. So what I'll do is I'll read in my 2D ligands because this is a result file and not doesn't have the ligands there. And I'll run the same settings as before. So I'll just do the rule-based treatment. I'll read in all those 2D ligands. So you can see I have my ligands, and I'll uncheck the crystallographic one. So you can see I've got my ligands there. And so I've got these 2D ligands, and these are the crystallographic ones to be redocked in to prove that it's working. In this case, because I want to dock into multiple proteins, the only difference I do compared to the conventional docking step is I'll actually simply select all of the proteins that I want to dock into. So here I've got all of the different crystallized structures of the same protein. So the BTK protein, they just have different ligands co-crystallized within them. I'll go back to my docking menu. I'll select ensemble docking. And actually I have as you can see, I have very similar options available to me. So I will use normal again, but all the other options are available in terms of accuracy throughput, speed. I will use the selected 6 ligands that I want to dock into. You can see in this case, actually, a grid has already been computed and is saved within the project file, so I don't need to do that step. I can use the existing grid, or I could actually select the ligand and generate a new grid. If you do have a case like this, a tip actually is to use the largest crystallographic ligand of the set you have. So you can see we've got a number of different sizes here. So the bottom or the second ligand would be good options because they're the largest ones. And the grid is set up when you select a ligand. It's actually the ligand plus 6 angstroms, the residues within 6 angstroms around the ligand by default. So selecting the largest ligand generates the largest grid. But obviously that's relevant to the size of the ligands that you're actually docking into the active site. Beyond that, the other options are the same, except we have all of the proteins present here. The same thoughts need to be given to whether you have waters or not in terms of including them in the active site. And I can copy them again. And all of the other options are also still available to you. And then I will simply click Start. And you can see here, actually, there was one without a grid. So one of the proteins didn't have a grid, so it's generating that one. And I can see what it's doing here. And then it will actually start docking into all of those proteins and keeping the best scores. Much like before, I'm actually going to cancel that and read in the results. So I'll simply cancel that and then read in the results. And so when I look at the Ensemble docking, it looks very, very similar to previously. So I've got poses for my ligands in my ligand table, but the key difference here is you can see I have the poses for the ligands. They can have different proteins associated with them, and the scores are relevant to those different proteins. So you can work through those and look at which protein conformation is best suited to your ligand. Again, you can look at each one. One thing I would do here is from the view menu, when you have this instance, is actually if you use synchronized selections, then as you change, looking through each of the poses and the protein changes, the selection within the protein table and shown in the 3D window is automatically updated. So we can actually look at the different ligand poses in each of the different ligands without having to reselect them manually. So, but all of the other all of the other structures the same in terms of the fact you have these 3 scoring functions present in the results. So after showing you Ensemble docking, what I'm actually going to do now is talk about Covalent docking again, and just to make it slightly easier to reintroduce that, what I'll do is I'll just show a couple of slides and then we'll actually do Covalent docking again. So this workflow is very similar to the conventional docking workflow, except in this case it's very important that actually the ligand going to be docked into the active site has to be the electrophilic reactive compound. So what does that really mean? So in the example I'm going to show you, again, it's the BTK kinase that we're going to dock into with ibrutinib as an example ligand. So this is actually the reactive compound that's dosed to the patient, and it reacts with a cysteine in the active site. And this is the product that you end up. So you end up with the loss of the double bond and a formal covalent bond to the cysteine in the active site. So with covalent docking within FLAIR, you start with the same compound as you would use to treat the patient. And this is the result that you get. So you don't get a formal covalent bond to the protein, but you get this sulfur added to the carbon here. And the sulfur has the same coordinates as the cysteine in the active site. So actually what this does is it allows you to have lots of ligand poses, lots of different ligands that you can dock at the same time. And any of that are of interest, you can very easily generate a formal covalent ligand protein complex and perform other studies on that. So what we're going to do is I'm going to download. I'm going to actually take this I need to turn the filter off. So what I'll do is I'll actually take my ligand, which is here, which is my covalent ligand. I'll just turn those other ligands off, and I'll select my relevant protein, which is this one here. So here, you can see, here you can see my ligand that was taken from the PDB, and when you download this 5PJ crystal structure and you run it through the protein prep, what happens is actually the protein prep makes the protein itself wild type, so it breaks this double bond, so it makes the cysteine, the covalent bond from the cysteine back to just a conventional cysteine, and it simply puts a proton on the ligand, so it's there in the active site. So this is actually the co-crystallized covalent ligand in its protein, but you don't see the covalent bond between these two atoms. So what I'm going to do is I'm actually going to dock into this protein, and I'm going to again use a 2D small molecule structure. So I'll load that one in. So in this case, what I've got is a 2D structure of ibrutinib, and I'll load that in. I want it to be 2D. So you can see here, I have my 2D structure, and that's what I'm going to dock into. But you can also see I've got my Michael acceptor here ready to use. And I will set up the docking in a similar manner. So I've got my co-crystallized ligand that I can use to help define the active site, and I've got my protein available and set up because it's been prepared. I'll go to the ligand menu, and in this case I'm going to use covalent docking as my workflow. So you can see here I've actually got a grid defined already, but if I wanted to define it for the first time, then what I could do is I could actually select my co-crystallized ligand as a reference point to find the grid. And the only difference in the workflow itself is you need to define which residue that you're going to form a covalent bond to. So if I have a quick look, I can actually see that is cysteine 481. So I've got a choice of cysteine, lysine, serine, or tyrosine. So I need to use cysteine, and then I can select which cysteine residue it is from the protein structure. So it's 481, so I select that one. And then I'm ready to actually set up and start generating my grid and do my docking. I'll quickly use the existing grid to make it easier to run through. No, it's not been defined. Okay. 481. And I just click start to launch that application. All of the other options in terms of accuracy are still available to you, and it's still relevant in terms of getting best performance. It would make more sense because I've only got one ligand that I'm docking here to actually use a much more accurate approach rather than the normal method. But this is just a demonstration that I'm showing you here to use that. Whilst that's actually running through, I would say what you do need to do is look at the results, not just look at the docking scores. So I'll actually cancel that and read in the results. This from this file. So here I've got my docked ibutranib ligand from this 2D structure here, and now I've got my co-crystallized form of the same ligand present. I'll just make the 3D window larger. So you can see actually here, it reproduces the pose very well. If I just show them exactly superimposed, then actually the pose is very good. The only difference is between the green structure, which is the co-crystallized one, and the magenta colored one, really is around the orientation of this carbonyl. And actually, the reason why this is different is the magenta structure was docked in a dry active site, so there were no waters present. And this carbonyl in the co-crystallized structure actually forms a hydrogen bond with that water molecule. So that's the reason why you get this difference in terms of where the carbonyl is. And it also illustrates the importance of paying attention to the protein and ligand setup, and thinking about where residue rotamers are. Are they relevant? Do they need to change? Is the protonation state correct? Or should waters even be present in the active site or not? Fortunately, docking is very quick to do, and so if you validate your docking protocols on with a small number of compounds, you can try a number of different options and see which provides the best results. Again, the covalent docking also generates a number of different poses, and it has the rank score, delta G score, and the VS score generated for all of those poses. And you can look at the alternative poses. Maybe there's a better one. Actually, you can see here the second pose much more accurately reproduces the crystallographic ligand. And in this case, there seems to be a difference in the rank score. But again, this is really driven because of this water is not present in the docking workflow that was used. But the delta G scores are pretty similar. If we wanted to use that one, just like before, we could select it and then collapse the different poses, and then it would be shown as the default ligand. There are some tips that I would, with covalent docking, it's actually a very sensitive docking process. So actually, if you don't get good results, some of the things you can try is actually changing the size of the grid. So using the atom selection to define the grid size, both making it smaller and bigger to see if that affects the results. You can also try docking a fragment of the reactive compound and then using the conformational Hunt and ligand alignment to superimpose the full ligand on the good fragment docking result, or you can look at amino acid rotamers to create or remove steric or electrostatic clashes, and you can try using constraints as well. So that's covalent docking. So actually now I'm going to show you template docking. So what I'm going to do is I'll just close those ligands. We'll go back to one of the other conventional ligand protein complexes. I'll read in that file of 2D ligands again. So I'm going to read in, in this case, I'm going to read in this file, template ligands for 2D. And I'll again apply the rule-based protonation for my prep, keep all of the 2D ligands. So if I just show you these two where are we? Take those ligands and I've got some 2D ligands present here that I'm going to actually do some template docking with. So what I'll do is I'll set up the docking run much like before. So I'm going to just do conventional docking. As I mentioned before, you can use template docking in Ensemble docking. So you could use it to dock into more than one protein ligand complex. If you do that, then you do need to think about what crystallographic ligand you will use to perform your ligand superimposition. But it does make more sense to use template docking when you've got a congeneric series, and so it should be an easier problem. So I'll select my docking option. And in this case, what I'm actually going to do is, and I've already got these two ligands selected, so they're the two I'm going to dock into. I'm going to set up my grid to use this structure, so this covalent ligand itself. So I'm going to dock into that area of the active site, and I'll take the same protein. A grid has already been created, but I could just take these settings here and use that. And I want to use template docking, so I'm actually going to select that ligand itself. So this is the co-crystallized ligand, and I'm going to use that to do a ligand alignment first, and then those results will be fed and used for the covalent docking. Okay. So because I've already got a covalent docking grid, that's not compatible with doing non-covalent docking. So I will have to generate a new grid. So I'll do that. So I'll click start. And you can see the order of things is slightly different. So first you align the ligands, and then you do the docking step afterwards. And I could let that run through, but I'm not. I'm going to cancel that and just jump to the results. But you can see within a few minutes, actually, we would have results available. So I'm going to take those results, and I read in the results. So here I've got my template ligands in 2D and the results, the docking results from using templating. And just like before, I've got my arrow to look at the different poses. So I've got the crystallographic pose itself shown. And if I look at the results, then I can show you how they fit, and we can independently, so you can see how they've been superimposed and looked at in terms of generating those poses. And if I just expand this single set of ligands here, you can also look through the different results from the docking and using this template in and look at the RMSD. So you can see how the core is nicely aligned here. There's been some changes in terms of optimization there, but that's really because this ligand isn't a covalent ligand. We haven't done covalent docking. This is a conventional ligand, and so it can't get too close to this cysteine residue, and that's why we see the differences on the side. Finally, with respect to docking, I'll actually show you how you can use constraints to bias your results. So what I'll do is I'll actually I'll set up a constraint here. So I'll turn off, I'll just look at my crystallized ligand. So if I look at this ligand in the active site, I can see I've got a hydrogen bond present from this amine to this carbonyl in the back in the protein. So let's say I want to ensure I have this hydrogen bond, so I can set a constraint for that specific carbonyl. So what I do is I pick the carbonyl atom from the oxygen. I go to my ligand menu, and I have constraints as part of the dock and align options. And I can add a constraint to a docking constraint to the protein atom. So this throws up this little menu here. So I've already selected the atom that I want to put a constraint to, and I have some options in that I can have a weak constraint, a normal constraint, or a strong one. And that just varies the strength of that constraint in terms of how tight it has to be. So I'll just use the normal option. So I've added a constraint to this atom, this carbonyl atom. And now my constraint is actually set up to be used for using docking. So in this case, what I can do is I can just dock some ligands again. So I'll go back and I'll select these two ligands here and just click dock. I've already got a grid defined, so I don't need to set up a new grid. The constraint is already included and isn't an option I have to select and use. I won't change the method, but just like before, all of the methods are available to be used for accuracy. And you can also have a template ligand defined if you so desire. And again, you can copy the ligands. If you don't copy the ligands, the results will actually be written over the entries in the ligand table. So now I'm ready. I'm just going to click start, and that will run through and do that docking for me. And whilst it runs through, I'll just So whilst that's running, then we can talk about use of constraints. So we would recommend you don't put too many constraints in. So typically constraints 2 to a maximum of 3 perform well. If you add more than 3, then you start generating such a strong bias that some ligands won't be able to fulfill those constraints and you won't get good results. And it makes sense to spread the constraints out over the active site, so you have so you help bias the poses nicely. In terms of looking at and obviously you can use constraints in all of the different docking up workflows, which help give you nice good results. In my experience, using constraints is certainly a useful thing to do when you have experimental information that suggests something is important. So that could be a a co-crystallized ligand that always sees an interaction, or it could be SAR that actually makes sense to you in terms of the interactions that that compound would make in the protein itself. So that's actually docking itself, and so I'll leave that running now, and just I'll just introduce electrostatic complementarity, and then we'll look at the results there and looking at electrostatic complementarity analysis. So a few slides on electrostatic complementarity. So one of the examples we're going to look at is a biotin streptavidin example. So this is actually one of the most tightly bound ligands to a protein. And if you look at the left, you can see the solvent accessible surface of the binding site, and it's colored according to the electrostatic potential of the protein, which has been calculated using the Cresset Z force field. And on the right, you can see the solvent accessible surface of the biotin ligand, and it's also colored according to the electrostatic potential of the ligand in this case, but the ligand has been flipped 180 degrees so that you can actually compare the electrostatics of the ligand and the protein. And what you can see in general is you can see actually the positive potential in the protein matches the negative potential in the ligand, and vice versa. But you can, in FLAIR, you can use our electrostatic complementarity coloring on the surface. So in this slide, you can see the surface of the protein, and independently the ligand in the active site, colored by electrostatic complementarity, with green meaning a good complementarity, and then mapping to regions of poor complementarity or electrostatic clashes. And as you can imagine, this is an example of one of the strongest non-covalent interactions known in nature. The electrostatic complementarity of biotin towards the protein is almost perfect. So you can see it's almost all entirely colored green. So why is electrostatic complementarity important? Well, the electrostatics between small interactions between small molecules and their respective receptors are a key contributor to the binding free energy. So an enthalpic component. Assessing electrostatic match between proteins and ligands provides insights into why ligands bind, or what you might want to do to change the electrostatics to improve binding. And it informs also on the polar enthalpic design of polar enthalpic binders, which are typically been seen as providing better selectivity of pharmacokinetic parameters than entropic binders. How do we calculate electrostatic complementarity? So what we do, the electrostatic complementarity of a ligand to a protein is calculated from a comparison of the protein and ligand electrostatic potential values at all of the vertex points of the ligand's solvent accessible surface. Perfect electrostatic complementarity would mean that at each vertex point, the ligand electrostatic potential value would be paired with the protein electrostatic potential value of the same magnitude, but a reverse sign. In practice, for a vertex on the surface, the electrostatic potentials due to the ligand and due to the protein are computed. The vertex points distributed on the surface with a spacing smaller than 0.2 angstroms. Distance scaling points on the ligand surface which are too far away from the protein, from any protein atom. So in this case, it's greater than 3 angstroms, are scaled down by linear downweighting. The ligand protein electrostatic potential values are also capped to the maximum electrostatic potential values observed for water molecules to approximately correct for desolvation and are added together. The result is divided by the larger of the 2 potentials and linearly scaled so that a point where the ligand and protein electrostatic potentials are equal and opposite gets a score of 1, and a place where they are equal gets a score of -1, and a place where either potential is 0 gets a 0 score. In practice, what you can see is this is how it would work using the equation on the slide from point 5. So at each vertex, we look at the potential. We use the equation, we get the electrostatic complementarity, and then that's repeated, as I mentioned, across the surface of the ligand. And each vertex point is used to color the surface at that point. And actually you can take all of those values and average them across the whole surface and generate a single score. And if you do that, you can then use that score to actually rank or triage protein ligand complexes. Within FLAIR, we've got 3 different scores that we provide with the electrostatic complementarity. We've got the standard EC score, which has been normalized across the surface integral. We've got the Pearson correlation coefficient variant of that score, and this can actually provide a better indication of ligand activity in some cases, but is a bit susceptible to noise. And then we have a Spearman variant as well. And this one often provides more robust results against background electric fields, but it can be biased by a large net charge on the protein itself. So I'm actually going to jump back to FLAIR itself now and show you electrostatic potential results. So you can see here we've got our docked ligand results using our constraints present in the protein, and you can see that all of the results actually have a nice hydrogen bond to this carbonyl. So now I'm going to go to a different example and we'll look at the electrostatic complementarity. So in this case, I've got a different protein system with a ligand bound and present. And what I'll do is I'll first look at the contacts of this ligand. We'll look at the conventional electrostatic potentials and then the electrostatic complementarity. So if you just quickly if I show you the contacts, you can see we've got some hydrogen bonds between this basic nitrogen, between the carbonyl and this glue side chain. We've got some hydrogen bonds from the carbonyl to a backbone NH and a threonine side chain. And then we have other interactions shown from within the protein and water complex there. The indolene ring itself is actually surrounded by a lysine, a glycine, and a tyrosine here, but we don't see direct hydrogen bonding interactions there, of course. So if I just want to look at the electrostatic potential of the ligand itself, I go to the ligand menu and I add a surface. I can add the electrostatic potential surface, and so I can look at my ligands electrostatics there. And so the blue area is showing negative electrostatics and the red positive. I can also look at the electrostatics of my protein. So if I go to my protein menu, I can add a surface there. So what I like to see is the electrostatic potential. You can actually change the coloring scheme if you want to, and you can also have a wireframe view of the surface too. I'd recommend you use one of the higher quality for the visualizing the surface, and I just use low simply in the interest of time. And I'll just look at the visible atoms, and in this case, I'm include the cofactors, but I'm not going to include water for my surface. So I'll simply add that surface to the protein. So now I have my electrostatic potential surface shown on my protein and in my ligand, and I can look at how this blue area is complementary to this red area of the ligand, and I can see that also this negative area for my ligand may well fit against this region here in my protein in the active site. Possibly I have some clashing on the edge face of my indolene ring here against this surface of the protein, and it looks more like there's a bit of a clash here as well. Sorry, good complementarity here. But that's often quite hard to really look at that, and you have to twiddle around the protein a lot to really, and ligand to see the where there is clashes or matches. So if I just turn off the surface for the ligand, the protein, and change the ligand surface to the electrostatic complementarity to the protein, and because this is a co-crystallized ligand, it's already assigned to this protein. If it was docked, it would also be assigned to that protein. And I'll just show this surface here. So now you can see very easily where the protein and the ligand have good complementarity and where there's some clashing. So you can see that we do have some clashing between the pi electrons of our ring system here and this carbonyl, and the edge also has some minor clashing of electrostatics, whereas where we thought we had good complementarity, it's easy to see we do on these surfaces here. So, but note the if you had other proteins and you wanted to change them, you can actually go to the ligand table. So you can see here, this is where the protein association is shown, and you can right click and actually change the protein by this set protein option, and we'll actually do that a little later. So we've looked at how that single ligand can have some good interactions or clashes, and it nicely reproduces the clashing between the pi electrons of the aromatic ring and the carbonyl. So what you might want to do in terms of design is actually some substituents where electron withdrawing would be beneficial, or maybe a different heterocycle, which was a less rich electron ring. And the positive clashing that we're getting on this side, you could actually, sorry, the positive clashing on the end here in terms of the sigma hydrogens, what you could actually do is maybe a more negative ligand electrostatics would actually be beneficial. So appropriate electron withdrawing groups to help make those less positive. Change that so you could have not have the so positive protons there. And this actually fits nicely with the original data from the Aztecs paper that this work is based on. So what I'm going to do is I'm actually going to, this is just one ligand, but I'm going to read in a number of other ligands and look at their electrostatics. So what I'll do is I will just open this set of ligands here. These ligands have already been pre-aligned and pre-processed, so I don't need to change them or change the protonation state. I just need to read them in. And you can see that actually this ligand set is a set of ligands with small changes where in the ligand, in the original ligand itself, to try and improve the complementarity, make changes there. So what I'm going to do is, because I've read these ligands in, they haven't been docked or anything like that, because they've actually been aligned by an MCS in Forge. The ligand alignment is now available in Flare, and that could be done here rather than have to use Forge. And they also have their activities. So I'm actually going to move the activity across so it's a little easier for me to use and show you. So I've got some activities present, ranging from fairly active to much less active. So this is just a micromolar IC50. There is a PIC50 as well. I'll move the PIC50 over. But because the ligands have come from outside of Flare, you can see in the protein column there is no association of these ligands to any proteins. So what I'm going to do is I'm actually going to define that, and then I'm going to generate the electrostatic complementarity. So they're all selected here, and I'm going to set the protein to my prepared protein here. So I've only got two, the original crystal structure and then the prepared one. I'll select that there, so you can see now this field is fully populated. If it isn't populated, it needs to be set when you ask to add the surface. So I'll generate the electrostatic complementarity for those ligands to that protein, and then they'll all be displayed across there. Just wait for that to complete. So you can see now I've got the complementarity for all of those different ligands. The first one is actually the crystallographic ligand, and then the others are the designs afterwards with the names suggesting what's happened. And what you can see is actually, as we make some of these changes, their effects on the compounds themselves. So adding the NH in this position itself hasn't improved the electrostatics. It's electron donating, which makes the pi cloud above and below the endoline more rich, which is not really what we want to do. The same is true for the methyl and methoxy versions. So the methyl and the methoxy versions, they're not improving our electrostatics on the aromatic ring set. And there's an increase of a clash, not just with the pi electrons from the carbonyl and the aromatic ring, but also you can see on the edge, this is more of an electrostatic clash with these variants than the original compound with the halogen present. And this is all well in line with the Hammett's sigma para values, and accordingly, these substituents are also fit with a weaker PIC 50. So you can see the amino one is significantly weaker than the original chloro compound. Whereas when we add other electron withdrawing groups, so you can see the fluoro and is good, and the chloro is the same as this compound here. You can see it's beneficial. But I mentioned in the slide set you can actually average the values across the surface to generate a single score. So that can be done. If you actually are going to use the EC score itself, you need to pay a lot of attention to the protein setup. We found this is actually very sensitive to the protein setup. So use the flare protein preparation first with default settings, and then you want to check and possibly correct the protonation states of amino acid side chains. Check and again correct, if necessary, amino acid side chains with flippable or tautomeric forms, such as histidines, in close contact with the ligand. And then once you've done all of that, you should actually test which orientation of the side chains yields the higher EC scores and keeps the best result for the respective ligands. And look at the heavy, and pay a lot of attention to heavy atoms within the 3 angstrom distance criteria from the protein to the ligand. When you look at the ligands themselves for use for EC scoring, you should carefully check the protonation state of the ligand. You can manually build an X-ray ligand or a substructure alignment over docking is often preferred. It reduces the conformational noise, because if you use a substructure alignment of the ligands, you get a much tighter alignment of the ligands than you observe with docking. And that's available within Flare. And you should look at the optimal orientations of substituents as well. So if there are multiple orientations possible of ortho and meta substituents on aromatic rings, you should explore the effect of those orientations with the EC score, and then use the best orientation, the orientation with the highest EC score. In terms of water is also very important. So the relative orientation of waters in the active site is important. The waters themselves are mostly dynamic, so you should only keep waters inside or near the binding site that have a strong orientational preference. So that really means you want at least 2 hydrogen bonding contacts to the protein, or at least 1 hydrogen bond to the ligand and the protein. Bridging waters interactions may only be possible for sim ligands, so you should create different states of the protein, one with a bridging water and one without. And if the ligand doesn't possess the required hydrogen bond acceptor or donor motif, then you can select the relevant protein that you want to use. So if you have a compound that does form the is capable of forming a protein hydrogen bond interaction, you'd obviously use the protein you'd set up with the water present, and if not, the one with it absent. And you may need to re-optimize water orientations as well in case of suboptimal hydrogen bonding networks. So a lot of that work is and knowledge has been carried out by scientists within Cresset and has been published. So if we want to generate the scores, actually we just simply click this button here for electrostatic complementarity score. So we click that and it computes the values, and then those values are assigned and placed within the ligand table. And because these are not multiple alignments, it's just a single compound, there aren't additional poses to look at. But if this was a set of docking results, or preferably some alignment results, you'd have scores for each of the alignments. So we have those full EC scores, and from the extensions tab, I can actually look at a plot. So what I can do is I can put the EC score on one axis and the PIC 50 on another. And if I do that and just look at the default EC one, I can see I've got a trend for most of the compounds, but actually the sulfonamide is methyl sulfone is an outlier compared to all the others, and that's actually that's interesting. But why might that be? And if I look at that one, I can see actually I've got a lot of electrostatic clashing with my methyl sulfone. And if I just display the protein again and look at the protein in the protein and ligand complex, then actually what I can see is I've got a clash with this lysine residue and the sulfone, methyl sulfone itself. So that's probably some of the reasons. So I've got some sterics and electrostatic clash in there. So what might I do if I have that as an example? Well, what I might do is I know that lysines are flexible, and it wouldn't expect this residue to be in that conformation, that rotamer with this ligand bound. I know that this ligand is actually an active compound. It's got a reasonable PIC 50. So clearly it must fit in that active site. And you can see the clash in there itself. So what I do know is actually there are more than one protein crystal structures available with that for BTK kinase. So what I can do is I'll actually get another protein structure. So if I open that other structure, so it's already been prepared. So I'll just open this prepared PDB and I'll read it in. So now I have an alternative protein structure. And if I show you put my sulfone back on there again, and the other structure, just look at the active site. So I can see I've got a difference in my lysines in terms of where they are spatially. The rest of the structure looks pretty much identical, but that lysine residue is moved. So what I can do is I can actually change my protein here. So I can change the proteins to the other one. And now I can, so it's automatically recomputed my electrostatic complementarity on the surface, it hasn't automatically changed it in the table, however. So these are still the EC scores from the other protein. So if I recompute those now, and I'll close that and replot my results. And actually I can see, whilst I don't have a super tight correlation, I actually do have a much better correlation, a trend, and I don't have clear outliers. So I have this trend in terms of the effect on activity. And really I should also look at their effect on I could look at the other EC scores. So this is just the standard EC one. So I could actually look at the other ones to see how they might behave. So I'll just take those, look at those as well. So actually this one still has a bit of an outlier there. But I could hopefully, but here is, I can see a much tighter, this is the best relationship I have with the EC Spearman coefficient option, with a reasonable R-squared. It's certainly good enough to help me rank order my compounds. So I've finished my demonstration of flare. Are there any questions? And that can be questions for docking or for EC.
Giri, you're there?
Sorry, Krish, there was some issue. I'm back. Can you hear me?
Yes.
Yes.
Yeah.
Oh, sorry about that. My internet, some issue was there. Okay, so there are a few questions, so let me pick that up. Okay, so the first one is, if there is an error in protein structure, such as missing loops or side chains, how that could be rectified with your tool?
Okay, so fortunately, when you load in a protein, you have a protein preparation step, which you can also access from the protein menu as well. So it's here, this protein prep step. So in the protein prep step, one of the things that it does automatically is if there are missing residues with incomplete backbone, those are deleted, and you can remodel those in afterwards through different mechanisms. If there are 1 to 2 residue gaps in your protein, then the protein prep step will automatically bridge those gaps and fill them in. If you have other gaps that are longer than 2 residues, actually within the extensions package, so these are actually a series of Python scripts that you can download from the Cresset website. There's this option here to build loops with Freed, which is a package that's been developed at the University of Oxford. So here you can actually insert a sequence and build missing loops. So the combination of the two, you can actually set that up. If you need to change residues proteination state or flip their tautomer, then you have options here in the protein modifying area. Or if you really have to, you can actually get in and edit atoms and change bond orders through the edit function in the protein menu.
Okay. Another question is that how can a user could export the result of the docking poses or complexes that could be used as an input in other softwares, for example, GROMACS or for molecular dynamics using open source?
Okay, so you can simply select the ligands that you're interested in exporting, and you can export the ligands. So you can export them as either the selected or all ligands. So you have some options here, and you can also select the different conformations as well. So you can actually preserve the different poses. So you can actually keep the different poses, and then from that file, you can then it can save an SDF file, for example, and you can read that into any package.
Okay. The next one is FLAIR identifies peptide-like inhibitors as protein chain while the user was using, and how to define that as a ligand.
Okay, so if you had, if you imagine this entry here was identified as a separate peptide chain, but it was your ligand, you can actually either left click and drag it into the ligand table, which will then make it a ligand, or you can right click and yeah, that's the easiest way, is just to select it and drag and drop it into the protein, into the ligand table, and then FLAIR would consider whatever you've moved into the ligand table to be a ligand.
Okay.
You can also push things from a ligand back into the protein if you so desire, using the same thing mechanism.
Okay. Another question is, if we don't have info about the co-crystallized ligand, but we have the knowledge of the cysteine residue that participate in the covalent docking, how can we design the ligands that may target this particular receptor or that residue?
Okay, so that certainly is a slightly harder workflow in terms of what you would need to do. So you can still use the covalent docking to sample that, but what you might need to do in terms of a workflow itself is you certainly may need to have a number of different proteins with the cysteine in different rotamers, or if it's very obvious what rotamer it might need to be to accommodate the ligand to form a covalent bond, that would be my first choice to explore. And actually what I'd do first is I would probably work with a smaller, just the warhead and a little bit more of the ligand initially first to help better define in the active site. But certainly you can do that. So you could do that first step, then maybe align your full compound onto that substructure unit, and then look at how you might need to move other residues around or even the cysteine around to accommodate your full ligand to actually do that.
Okay. Another question, like how could one identify the MD analysis of RMSD in FLAIR? Can it be possible to determine the contact of protein with the ligand interactions in MD simulations within FLAIR?
Yes, it can. So FLAIR 4 has more functionality around analysis of molecular dynamics. So by default, you do see an RMSD from the original coordinates before you start the MD calculation. And you can see the RMSD compared to that in your simulation over the course of the simulation. You can also look at the contacts of that, of the ligand with the protein over the whole course of the MD simulation as a separate view. If you're interested in that aspect, I would recommend getting in touch with Krish and we could follow up on helping share some information around MD analysis.
Okay. And the question, something similar to that, probably this will be the final question because of the time limit. There are a few more questions also. So this final question will be, after minimization of protein structure, there might be some errors or some violation in Ramachandran plot. How could we rectify such errors?
That's a good question. So, one approach could be looking at running some MD, or you could run some additional minimization itself. Of course, the other option would be to manually edit the residue rotamer to ensure that it did fulfill the Ramachandran plot criteria. So you can do that through the editing option within the protein menu. You could also try mutating the residue to an alanine, for example, and then mutating it back to the residue you are interested in. That's another workaround to be able to optimize interactions, but also get a good Ramachandran plot for a residue.
Okay, great. Thank you so much, Nathan, for patiently answering all the questions. And I also thank the opportunity given by the drug discovery training program team, and also thanking Krish, Sidhuji, and everyone who has coordinated for the Cresset session. But if you have any concluding remarks for Krish as well as for Nathan, please go ahead, and then we can go ahead and conclude the session.
Giri, I just wanted to say, like, if there are any other questions left that was not asked today, they can always write to our support, and those will be answered.
Okay, absolutely fine. So a few more other things that to be addressed here is part of drug discovery hackathon. Many of you were having questions regarding the registration process. So we, with the team, we checked and we confirmed. If you have any issues that if you have registered as an individual and you wanted to again re-register as a team, or if you registered as a team but you want to register as an individual, later you change your mind, please keep in mind you have to register with a different email address, because there are plenty of registrations happening. So in the back end, we will be having technical glitches to identify that. So it is always better to use a different email address and then register as a team or an individual if you changed your mind. Now, if you have any issues on as a team, you are not able to register as a mentor or others, then you can always write to the official email address, which I'm going to show you in my next slide. So which will be ddh@aict-india.org. So there with the screenshot, you will be able to rectify what is the issue, that even though you got a registration link as part of the team or as a mentor. So I again repeat, for most of the questions, even today in the sessions, in the live chat, you have questions that you're not able to get the answers for the queries you asked. We have checked with the team and we got a response that most of the queries, even almost 99% of the queries have been responded. Please check your spam folder also in order to see. And as I already requested, please register with another email address of your own to register if you may change your mind from individual to team or team to individual. So with that said, I once again thank the speaker, Nathan, and all the other organizers of this Cresset session, and also thanking the training team from NEAST, Virtual Tool Room, and others. And soon, all the participants will be getting to know about how to get access to the licenses of different tools from different partners in the Virtual Tool Room. So that's all for today. Thank you so much. Have a great evening. Bye for now.
Thank you, Giri, and thank you, organizers of DDH, for giving us the opportunity for doing the session today. Thank you, Nathan, for the time taken for doing the session.
I wanted to say thank you as well. It's been a pleasure.
Thank you.
Thanks a lot, Hriday and Giri, for the support.